All right, let's get started. Thank you for coming. My name is Randy Shoup, and we're going to talk about scaling your architecture with services and events. Before I start, though, the conference organizers asked me to ask you to please ask me your questions through Slido, right? So very happy to do it if people can't do that or won't for whatever reason. Happy to do it in person if we have time at the end. But if you use Slido, sli.do, that's a great way for everybody being able to upvote and downvote the questions, and so we can get the most important things answered. Okay, does that sound good? It's okay to nod. Great, thank you. Cool, all right, scaling your architecture with services and events. I'm going to talking about my background for 2 seconds because it's relevant to why these lessons matter and how I've learned them. So right now I'm VP of Engineering at a company called WeWork in the United States. We are co-working spaces all around the planet, 30 different countries, and my team is responsible for building a bunch of the member experiences, but overall we're essentially cloud, but for physical space, so think physical space as a service. Before that, I worked for an American company called Stitch Fix, which probably very few of you have heard because we were not yet in Europe. But I spent about 2 years building the engineering team there to use a ton of software and data science to try to decide what kind of clothing people will like. Before that, I worked at Google on Google App Engine, so that's Google's platform as a service like Heroku or Engine Yard or Cloud Foundry. And then before that, I spent about 6.5 years at eBay as the chief engineer, helping eBay transition itself through multiple generations of its infrastructure. And I say this because like a bunch of these lessons are things that I've actually learned, and mostly I've done wrong. So here you can take advantage of the lessons from when I used to have hair. Cool. So we're going to start by talking about like how companies might have migrated to microservices, because probably the companies that you know and love most, you don't realize they actually all started as a monolith. So eBay, depending on how you count, is now on its a complete rewrite of its infrastructure for the 5th time. 5th complete rewrite. So it started famously as a weekend project by the founder, Pierre Omidyar, over a Labor Day weekend in 1995. He was a software engineer at another company. He was not yet a billionaire founder of an internet startup. And he wrote that thing in monolithic Perl. So every item was a file. Everything sat in the file system on his own little personal machine. I always want to say on his laptop, but in 1995, I guarantee you he didn't have a laptop. He had some like 486 tower with 2 megs of memory or something like that, right? Sitting under his desk, churning away with a big fan. Cool. So that was the first iteration of what later became eBay. The second iteration was built in C++, and particularly for the .NET and Microsoft folks among you, this was at worst 3.4 million lines of code in a single DLL. So if you guys think, we have a monolith, ours is the most terrible software in the world, it is not. It is not the worst monolith. That was. They were hitting compiler limits on the number of methods per class. Anybody know what that is? It's 16K. And I'm embarrassed that I actually know that because no one should have to know that you can have 16K methods in a class. And probably now it's 32-bit, but whatever. Cool, okay, next iteration was a rewrite in Java, and we couldn't really call it microservices at this point, but maybe mini applications. So there were 220 different individual Java applications, some large, some small, each of which served a bunch of the pages on the site, right? So there'd be an application for the search pages, an application for the selling pages, an application for the buying pages, does it make sense? Times 220 different kind of individual subsections of eBay. And then now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution. So it started famously as the world's largest Ruby on Rails app, which they codenamed the Monorail. I thought that was very clever. The next iteration was a pulling out of a bunch of the front end, mostly into JavaScript, a bunch of the back end out into services, mostly even in the early days written in Scala, because Twitter was a very early adopter of the Scala language. And then now it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. As of 1999, Amazon was also a monolith. It was C++ on the back end and this monolithic Perl Mason thing that generated the UI. So pretty bespoke, but also pretty monolithic. And basically, Amazon took the years 2000 to 2005 to rewrite that monolith into what we would now call microservices. They just called them services. But they used a lot of the principles and the techniques that we're going to talk about here. So does there look like a pattern here? It's okay to say, yes, Randy, there's a pattern here. All right, good. You're listening. So there are two aspects to this pattern, though. Nobody successful started with microservice, and I want to triple underline that. Like the rest of this talk is going to be about how to do microservice, how to do events, but if you don't need this stuff, if you're earlier on in that cycle, you should totally stick with a monolith. Like, don't hear me arguing the only way to do this stuff is services and events, but if you do services and events, I'm going to tell you how to do it. But past a certain scale, and legit, not everybody in this room and not everybody on the planet is ever going to make it to a scale where we need this. Maybe 90%, 95, 99% of the applications on the planet are completely legitimately written in a monolithic style, and then you should be perfectly proud and happy about that. But past a certain scale, the only way that large-scale enterprises work is something that we're now calling microservices. The way I like to say it is if you don't end up regretting your early technology decisions, you probably over-engineered. If there was some company that was an Amazon or eBay competitor in 1995 that instead of building a successful business on a terrible piece of monolithic software, instead what they did is they built some distributed system and didn't focus on their business, there's a reason why we've never heard of them. Does it make sense? Amazon and eBay earned the right to rebuild their architecture exactly because they focused on their business, and they built that business in the most straightforward, simple, stupid, like just simple way, straightforward, that was absolutely correct for that scale, and then they earned the right to rebuild it in a scalable way. Does it make sense? If they'd started out building the distributed systems that they ultimately evolved to, they never would have evolved at all. Okay, so the agenda for this talk is I want to talk about migrating to microservices, again, with the asterisk that maybe only 1% of you need to do this. Then I'm going to talk about, once we've built ourselves in a microservices way, what are some challenges that we have around data? How do we deal with joins? How do we deal with transactions? How do we deal with shared data? Those kinds of things that we really know and love in a monolithic application and a monolithic database. And finally, we're going to close with some thoughts around how to guarantee, and I'm going to use really strong air quotes here, guarantee end-to-end correctness in the system. How do we guarantee that the publisher of an event is writing its local state and also publishing it? And how do we guarantee that consumers of events do their jobs correctly as well? So that's the agenda. So let's start with migrating to microservices. So again, I feel like in 2018, we sort of need to say for 2 seconds what we mean by a microservice. To me, the micro in microservices refers to the scope of the interface. Micro is the scope of the interface, by which I mean the interface is single purpose, it is simple and well-defined, and that interface is reasonably generic so I can make it modular and independent. So if I write a payment system, that interface might be super simple, like Randy pays Debbie 100 euros with this credit card. Like that's basically a payment interface, right? And that payment interface I can use to pay Debbie, or that's an interface that I could use for suppliers, me to pay suppliers, or for my customers to pay me. Does it make sense? So that is a modular and independent, also a very, very simple, clean interface, but anybody who's done payment systems knows that there's a huge morass of stuff underneath that. Does it make sense? So what a microservice is not defined by is it's less than 200 lines of code, it's less than 2 hours to write, it's one developer times 2 weeks. Like, I don't feel like those things are all good properties to have. Like, I'd love to be able to write a payment service in 200 lines. I'd love to be able to rewrite every service in 2 hours, but that's not the defining characteristic. The defining characteristic of micro is the scope of the interface. All right, cool. And the other thing which is very important as background to the rest of the talk is the idea that each of these microservices owns its own data. Yeah? So at least logically, each microservice has its own sort of database. Now we can talk about what the physical implementation of that is. It might be some slice of some larger thing. It might be some piece of some cloud data storage mechanism. But from a conceptual level, the data that I have in my microservice is isolated, and nobody gets to write or read it behind my back. Okay. So I'm going to talk about how to extract microservices, and I'll use specific examples of the techniques that we used at Stitch Fix when I was there for 2 years. So our problem was that we had a monolithic shared database that tons of different applications used. And basically every interesting entity for the system was stored in the shared database. And so the details aren't super important, but you can imagine that we had 80 different applications and services, all using a shared database that had on the order of 175 different tables. Okay, so what we're trying to do is we're trying to decouple those applications and services from the shared database so we can manage those individual things as separate microservices. So the first thing, just to make it cleaner and just have smaller number of boxes and lines, I'm going to pretend that we had 3 tables and 2 applications. But again, as I said, it was 175 tables and 80 different applications. Okay, so step 1 is we're going to create a service. In this example, we're going to create a service around clients. And that client service is going to use the table in our database that we're going to call core client. The next step, this is the big one, is we're going to simply take all the applications that were using that core client table and have them use the service instead. Now, just because I moved those boxes and lines and it took me maybe 1 second to do that move, like this just represented engineer months or maybe even engineer years of work. So I don't want you to think that I think this is simple. There's a lot of work here, but there is no way to move forward unless we move through this step. Okay, so the step is everybody who's using that table is going to use the service. And then the next thing I want to say is that don't stop at this point. Because at this point, we have all the problems of a distributed system, yeah? Because now we took a thing where we were using one database and now we're using this other distributed system and that client service can fail. We have all the problems still of the shared database of a monolithic system, and we so far have not gotten any of the benefits of microservices. So please, 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 triple underlined with sugar on top, do not stop at this step as had happened when I arrived at Stitch Fix. Okay, so the next thing we're going to do is we're going to make sure that that we extract that client table out of the shared database. Does it make sense? Like now we've finally gotten up to the point where that client service can be modular and independent. Because if that shared database goes down, that client service can still operate. Does it make sense what I'm saying? This is the definition of done. The definition of done is that core data that is served by this service is actually out of the shared database. And now we do the same thing with other parts of our system. So in this example, we'll do that for items at Stitch Fix, and then we'll do that for styles, which is our representation of clothing metadata. And just to underline the point about the boundaries here, these are the boundaries, right? So the service boundary of the client service encompasses not just the application part, but also the data storage part. Same for the item service, same for the style service. Does this conceptually make sense? Cool. And again, as I want to say, those like quick moving of lines on an architecture or diagram, like each one of those moves was a serious effort, particularly that last piece where we extracted all the table out of the shared database, because that was where the rubber meets the road. You're like, oh, I didn't realize that all these different background processes and all these different batch jobs and all these different other things were using that table. But once we have extracted that table, now we are really in the microservice world, and now we can get the benefits of it. Okay, cool. Well, so we're done, right? So, wow, that was pretty quick. All right, see you guys later. No, we're not done. We have now solved a bunch of problems. Now our teams can move independently of each other. Now these different services are isolated from each other from a physical and logical perspective in our architecture. But now we've introduced some problems that we used to have solved for us in the monolithic world. So let's talk about those. So we're going to talk about how to deal with some of the challenges that we've just introduced. So first I'm going to give you a couple of architectural tools that we'll use to think about the problems. We'll use those as solutions as we go forward in this section. And then I'm going to talk about how to solve the problems that we just introduced, which is how am I going to deal with shared data, how am I going to deal with joins, and how I'm going to deal with transactions. Does it make sense? Are some of you guys thinking about these issues right now as you move to a service architecture? Okay, a few people. It's more like you need some more coffee, I think. All right, cool. So we're going to talk about those architectural tools. So the first of those architectural tools is thinking about a system as a system of record. So I'm sure anybody who's worked in an enterprise has sort of heard this phrase. So the idea of this system of record is that any piece of data in my system, whether it's about a client, it's about a package in Stitch Fix, or a customer, something like that, every piece of data is owned ultimately by one and only one service in my infrastructure, right? And that service is the canonical system of record of that data. So in this example, let's imagine we're talking about customers, and that customer service is the owner of the customer data. But of course, if we're talking about customers, almost every part of our system uses customer in some way. Does it make sense? Like, it's hard to do anything in our system without having some reference or some usage of customer. But every other usage in our system of customer information is a read-only, non-authoritative cache of that data. And every one of those words is important. It's read-only. So if I go and ask, I don't know, the billing service, what's the customer's address, it might be able to tell me, but it is not the system of record for that data, right? If I'm going to update the customer's address, it should go through the customer service. It's also non-authoritative. So if I ask the billing service, hey, what's the customer's address, it might be stale, right? Who's heard of DNS? DNS? Yeah. DNS is exactly this. Every place that you're, for the vast majority of places, if you're not the origin, you're interacting with a read-only, non-authoritative cache of DNS records, right? So this is exactly the model that the smart people that built the internet in the 1960s invented. All right, cool. So the next idea is using events as a sort of first-class citizen or a first-class concept in our infrastructure. So Wikipedia defines an event as a significant change in state. I like to think of it as a statement that something interesting occurred. A statement that something interesting occurred. So we're probably all familiar with the traditional three-tier system where we have some kind of presentation or UI, we have it over an application tier, and at the bottom there's some persistence mechanism, which is usually a relational database. But I think if we only think in the three-tier model, that we are missing a fundamental building block. This idea of an event or a state change as a first-class idea in our infrastructure. And one of the things I really love about the community of people that build stuff, and particularly more generally the community of people in the .NET world, is that you guys are way more likely than other parts of our software community to be thinking in terms of events and so on. So I really like that. Cool. So how do we combine services and events? So the way I like to think about it is events that I consume and that I produce are a first-class part of my interface as a service. So if I ask you, as a service owner, let's imagine, what's your service interface? For sure you're going to tell me the synchronous request response front door, right? You're going to say, oh, well, I take these operations and I return these results, something like that. And whether that's over REST or gRPC or DCOM or, God help you, Corba, you know, something, whatever it is, like you'll tell me that for sure. But what I also want you to tell me is what events you produce, what events you consume, and we're not going to talk about this today, but I also want you to tell me any backdoor bulk reads and writes from third-party systems, right? Extracts that you do out to analytic systems, bulk loads that you do from some third-party thing that you need to synchronize with. All those things, whether you like it or not, are part of your service interface. So the way I like to think about it is the interface of your service is any mechanism that gets data into or out of it. Does it make sense? Cool. Okay. So now that we have those two architectural building blocks, let's solve some of the problems that we just introduced with services. So the first problem we want to solve is shared data. Let's motivate the problem. So with a monolithic database, it's really easy to leverage shared metadata. I simply point at some shared metadata table, and then I'm easy and I'm ready to go, and I just join with it and it's fine. But where does that shared data go when I've broken this monolithic data up into individual microservices? Good question, I'm glad you asked. There are three different ways to deal with it that I've seen. There might be more. The first option is synchronously looking it up. You should feel no shame to do this. So let's imagine in this example that we have a fulfillment service at Stitch Fix. So we want to send packages to people with actual physical pieces of clothing in it that actually travel through the physical mail as actual atoms. So that fulfillment service is going to need to talk to the customer service to understand what the customer's address is, right? So that's something that we need to do. So it's a totally legitimate technique for the fulfillment service to ask the customer service in real time, what is Debbie's address? Totally legitimate. And we do this all the time. Sometimes, though, not always, but sometimes this doesn't meet our operational requirements. Like asking the customer service all the time is maybe too much load, or it's too much latency, or perhaps I want to be able to ship packages to Debbie, but without having the customer service up. Like maybe I'd like to be resilient to the customer service being up or down. These are all totally legitimate operational considerations that we might have or we might not. If we have those other ones, then I would suggest this other technique. So this technique, sorry that the diagram obscures a little bit of the words, but I hadn't not able to come up with a great word for this, so I call it an asynchronous event plus a local cache. If you can come up with a better words, please tell me because I'd love to use better words. So in this example, the customer service is still the system of record for the data. So it still owns Debbie's address. And the customer service, when Debbie updates her address, when she moves to some new place, it will send an event that might say, address updated, and the fulfillment service is listening to those events and updating a local cache of people's addresses. Does it make sense conceptually? So the owner of the data, that system of record, publishes an event, and then the other people that are interested in that data consume the event and store it locally. And this is a totally legitimate technique that we use all the time. Okay, and the third option for shared data, if it is small and if it is slow changing, like metadata, then you can use this technique by simply publishing this stuff as code. That's a totally legitimate technique for something that is slow changing and relatively small. So the examples I was using for Stitch Fix, like, again, it's about clothing. So Stitch Fix has models of like a size schema, so like small, medium, large, extra large, like the t-shirts you were given, you know, when you arrived at the conference. In the US, there are women's numeric sizes like 2, 4, 6, 8. Again, that's a separate size schema. Those things are very slow changing, right? So it's rare, not unheard of, but it's rare to introduce a new extra, 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 extra large. Believe me, we're working on it in my country, but that's fine. Colors, you would think that the color palette doesn't change, but actually over time it does. So not that there are new colors that are invented, but like new colors start to become really interesting. So there was a point in Stitch Fix where we introduced a first order idea of pink for men, but we couldn't call it pink, so it was salmon. But that was a thing that, you know, men started to wear a little bit more. So, you know, we would slow change those colors, fabrics. The US states, or maybe the EU member states, that is slow changing. It is not static, as we all know, you know, watching our news. Hopefully in the US, you know, Puerto Rico will become a state, and we'll try to start to treat them like citizens and real humans. Ditto EU, we'll see what happens, you know, over time about people coming in and coming out of the EU. We can talk about that over, you know, other stuff, adult drinks and all that. Anyway, but you can distribute this stuff as code. Does it make sense? Then it has a nice property of being versioned in source control, et cetera. But this doesn't work for customer addresses, right? Like I wouldn't use that technique here. Okay, cool. All right, so we talked about shared data. Now let's talk about joins. So again, let's motivate the problem. In a monolithic database, it's really easy to join tables. So I just, you know, add to my select statement, right? So now I say select from A, inner join B on some join condition, all good, very simple. But again, once I've split that data across multiple microservices, it makes joins really difficult to do. So again, now we have two techniques, and you'll see that they're very similar to the shared data techniques. So the first technique of joining is simply joining in real time at the client point. Right? So in this example, let's imagine that I'm trying to show an order history page to our customers, and I'd like to look up some data about the customer from the customer service, and I'd also like to look up some data about that customer's orders from the order service. So I would simply, you know, go ask the customer service with some customer ID, give me some metadata about the customer, and then I'd ask the order, you know, give me all the orders for this customer ID, something like that. And we would just join this in the front end. This is super simple. We do this all the time. This is basically every web page on the planet, right? Every web page that doesn't do one and only one call to the back end. Yeah? Cool. Okay. Totally legitimate technique. Again, why would we not use this? Maybe there are some operational situations where I want to be able to show that order history page if one or both of those services isn't up. Maybe it's too painful from a load perspective or from a latency perspective or from a data size perspective to make those calls in real time, in which case I can do option 2, which is what I call a service that materializes the view. And I'm very intentionally using database terminology here to give you some intuition about how this would work. So in this example, let's imagine that we're trying to get all the feedback that our customers have given us about the items that we have sent. So let's imagine that we send out this beautiful build stuff t-shirt to hundreds, maybe thousands of our customers. Each of them tells us that was wonderful, that was terrible, it fit me perfectly, I wish it was gold instead of silver, you know, something like that. We want to aggregate all that data. So in this example, let's imagine that we have an item service which represents the metadata about this build stuff t-shirt item. And let's imagine that we separately have a service which receives that order feedback from our customers. Each of those services could produce events, and we could listen to them and materialize the view, aggregate that join together, and store it locally in this item feedback service. Does it make sense conceptually what I'm talking about? Cool. If it didn't make sense, that's fine. Even if this theme seems unfamiliar, let me convince you that there are tons of systems that you use every day that do exactly this. So if you use one of those database systems that has a first order concept of materialized views, and that's basically all the enterprise databases like Oracle and SQL Server, et cetera. And when I say enterprise, it means the ones you pay for. Yeah? All right, cool. So those have materialized views, and materialized views work essentially exactly how I talk about. Almost every NoSQL system, so if you use Cassandra or React or Voldemort or one of the NoSQL systems, you're almost certainly pre-joining all the data before you do the write into one of those systems. If you use a search engine, so if you have an Elasticsearch or some equivalent in your infrastructure, almost certainly that is a join of a bunch of different individual entities in your infrastructure. And also, if you use any analytics system, any kind of data warehouse or something like that, almost certainly for it to be interesting, that analytics system is a join of lots of different tables from your database. Does that make sense? Cool. All right. Let's move on. Here's the hard stuff. So the next thing is, how do we deal with transactions? So let's motivate the problem. So in a monolithic database, it makes transactions across multiple entities really easy. So I just begin a transaction, whether through my programming language or in the SQL itself. I'm going to insert into table A. I'm going to update table B. I'm going to commit or roll back. That happens all at once or not at all. So it's atomic and consistent and isolated and durable. Wonderful. But once I've split data across services, it makes doing these kinds of transactions really difficult. In fact, it makes it so difficult that nobody really does them. We're going to talk about other techniques where you can kind of get at transactional-like semantics in a moment. But basically, nobody does distributed transactions at scale. But don't believe me. Believe Pat Helland, who's a wonderful and brilliant, actually former writer of transactional parts of SQL Server. He worked at Microsoft for 2 decades, something like that. He built the two-phase commit stuff in Tandem. Then he came to Microsoft and did it for SQL Server. So you can imagine what a big person he had to be to say, you know what, all that work that I did, people aren't really using it at scale. So I love the way he says it, which is, in general, application developers simply do not implement large scalable applications assuming distributed transactions. And being clever and funny and sarcastic, he has another way of saying it. Yeah, Pat's super cool. And you can read the paper that was referenced on the previous slide. It's called Life After Distributed Transactions, an Apostate's Opinion. An apostate is like a heretic. It's actually a convicted heretic, if you want it super detailed. But anyway, so what he said is he came around, he realized his sin, he confessed his sin, etc. He was reabsorbed back into the, into the fold, whatever. Okay, grown-ups don't use distributed transactions. All right, well, what do grown-ups do? Let's talk about it. Actually, before we do, who's heard of database isolation levels? Wow, I love you guys. This is awesome. That was like a half of the room. Awesome. Who runs at isolation level serializable? Let the record show that there were 2 or 3 lonely and wonderful people who raised their hands after that, after 50% of the audience raised their hand at knowing what they're talking about. So the reason why I bring this up, and if you don't know what I'm talking about, don't worry about it, it's not important. But serializable is the real transactional operation. And so anybody who's using isolation levels that are less than serializable, if you're using read committed or if you're using read uncommitted, why are you doing that? For performance. But what you are giving up is the transactional properties. So I want to let you know that even if you are in one big monster enterprise database that you paid for and you are not running it serializable, you still have these problems that I'm about to talk about. Okay, cool. All right. So instead of a transaction, since we're not going to be able to do it in a distributed way for reasons of scalability, for reasons of performance, for reasons of reliability, instead what we're going to do is we're going to do something that we call a saga, right? And being in the north of Europe, saga, hopefully that's, comes from you guys, not you guys specifically, but roughly this area of the world. Cool. The way we're going to do it is we're going to model the transaction we were trying to do as a state machine of individual atomic events. So what do I mean? I mean, instead of updating A and B and C in some ACID transaction that's all atomic, instead we're going to re-implement it as a state machine, or maybe less highfalutin computer science terminology, we're going to re-implement it as a workflow. So first we're going to do thing A. Thing A is going to produce an event. That is going to cause thing B to update itself, which is going to produce another event or set of events, and that is going to cause thing C to happen. Now you ask yourself, well, Randy, wait a minute. In the monolithic database, that happened all at once or not at all, and here, what happens? How do I do a rollback? Excellent question. I'm glad you asked. The way that you do the rollback is by applying compensating operations in the other way, right? So you tell C, undo yourself for some value of undo. It produces an event that goes back to B. B produces some events that go back to A. Does it conceptually make sense that the undo happens the forward part of the state machine happens at these series of individual atomic steps, and then the reverse happens as an individual series of kind of undo steps that go back to the beginning of the state machine there. Cool. The other thing you're going to notice is you can observe intermediate states, right? You can observe that we're in the middle of we've updated A, but we haven't updated B and C. We can talk about that later. There are techniques for dealing with that as well. Cool. Okay. Many real-world systems work like this. In fact, many of them that you use every day. So payment processing. So anybody who has paid anybody else, so let's imagine that I'm going to pay Debbie 100 euros with my credit card. Who thinks that that happens, in whose experience does that happen atomically and immediately? Let the record show that no hands went up. Terrible, right? That can't be. We have a distributed system. There's no transaction. What the hell? No, that's just how the real world works, right? So after 3 days, so I say, please pay Debbie 100 euros with this credit card. 3 days, that money is like not Debbie's, but also not mine, right? Do you know why like Wall Street has such the big buildings and London is so beautiful and like, are you getting the idea here? Frankfurt as well? Like all these financial capitals, yeah, the reason why they can build themselves is because they have their money for 3 days, have our money for 3 days. But there are reasons, and okay, and there's no transaction there. So let's imagine that my bank is Bank of America. Let's imagine that Debbie's is Santander or something like that you would have in España, and there's no like distributed transaction that Bank of America enters into and Santander does. It's like it's a series of individual events, and they do reconciliation at the end of the day, et cetera. Anyway, so payment processing works exactly like a workflow of individual atomic events. Expense approval. So when you go back to your home office, who has to submit expenses? Yeah, lots of people, right? Me too. And again, does that happen atomically? No, it super does not. I submit it to my boss, and she submits it to hers, and she submits it to hers, all the way up to the CEO of the company, and they say, no, Randy, you can't submit the expense for the jazz club that you went to with James because that's not going to work, and so I have to go and explain. No, it was really work. We actually talked about distributed transactions as we were listening to Miles Davis, that sort of thing. Anyway, all right, okay. Expense approvals, though. Yeah, so that's a workflow. So it goes from one approver to the next, and then back down. Great. Travel. So I came here, originally I'm from San Francisco, still am, that's where I live. I traveled from San Francisco to London, and then again London to Vilnius. When you asked, where's Randy? For a long time the answer could be in San Francisco, and then I was in the air, and I was in some transitional state. And you asked, where's Randy? And the answer is, he's in the air. Like where? I don't know, somewhere over Greenland or something like that. Does it make sense? And notice what's happening there is you can observe the intermediate state of Randy being between San Francisco and London, or equivalently between London and Vilnius. You can observe as a first order part of the travel system. First order idea is that you can observe those intermediate states. And what you should do is just model them. Say, Randy is in San Francisco, then he is in the air in some transitional state for 8 hours between there and London, and then he's in London and he's there for a while, and ditto a transitional state between London and Vilnius. Does it make sense what I'm saying? Model it as a first-class part of your interface. Don't try to hide it. Just embrace it and say, yes, we have a transitional state. Cool. And then the last thing is the software development process itself. So who writes code for a living? I love this conference that basically everybody's hand goes up. Raise your hand if when you hit return in your IDE, it is immediately and atomically deployed to your production system. Let the record show that no hands went up. Sometimes one hand goes up, and what happens is that person is editing in production. I do that, yeah, okay, let's talk separately. But the software development process, right? So if you tell me, Randy, I can't reason about a system where there's like one version of a thing over here and another version of a thing over there, it's like, dude, what do you do every day? Because there's version 10 of your software running in production, and there's version 11 on your laptop. And is that hard to reason about? No, it's just a little bit more complicated than everybody having version 10. Does it make sense what I'm saying? So again, this idea of intermediate states, this idea of eventual consistency, this idea of certain parts of the system knowing things that the other parts of the system don't, this is a first-class part of the real world that we experience every day. All right, cool. So a wonderful thing about these workflows is that they are very simple. They are typically, the implementations of those A and B and C things typically is very lightweight, it's very stateless, it's triggered by an event. So if you are still in 2018 wondering what in the world can functions as a service or serverless do for me, a thing, among many, but a thing that serverless could do for you is something like that. Does it make sense? Like if you're wondering, how could serverless enter into my architecture? How could I make that work together with microservices or the other stuff that I'm doing? One of many things that serverless could do well is this idea, which is stateless logic that is triggered in response to an event, does something very simple, potentially produces another event on the other end. So not the only way to do this, obviously, but a good and very simple and very straightforward usage of serverless, or I hate that term, functions as a service techniques. Does it make sense? Cool. All right, great. So the last section, I want to talk about other problems that we've introduced here and how do we resolve them. So the particular class of problem that I want to talk about, I don't even have the great words for it, so help me actually afterward refine the terminology here. But I want to talk about, the best word I can come up with, I was calling it guarantees, but actually in conversations with some of my friends at lunch yesterday, guarantees weren't working for people. So I'm going to try the phrase end-to-end correctness. But you're going to understand what I mean when I give you the examples. So what I'm trying to solve here is the problem of, I'd like to make sure that my system is eventually end-to-end correct and end-to-end consistent. And there's going to be a producer part of that and a consumer part of that. Okay, well, what do I mean, Randy? So the system level correctness in this system where there is a producer of an event, a transport or a bus that carries the event, and a consumer of the event is this. So we want to guarantee or have the property that the producer is going to produce the event. Yeah, so it updates its local state in response to something. It's going to produce the event. We want that. We also want that the transport is going to deliver the event. And we also want the property that the consumer is going to correctly eventually process the event. So these are, I haven't solved any of these problems, but can we see that this is the properties that we want? Yeah? End to end, to have a correct system, I want to make sure that the producer is going to produce the event, the transport delivers it, and the consumer processes it. Okay, cool. Let's break it up into two parts because there's a producer side and a consumer side. And before I do that, I want to say that just like that transaction thing, these are distributed coordination problems, right? It's a problem of I want ultimately the whole system to be consistent, and I'm trying to figure out how I can coordinate the producer side and the consumer side of my system to make it correct. Okay. Great. All right, so first I want to talk about correctness or guarantees from the producer perspective, and then we'll talk about the consumer side. So the problem, let's be very clear, the problem is that as a producer, I want to write my own little state change to my local database, yeah, and I also want to make sure that I send the event. Does it make sense? Note that these are two different resources, right? Typically, it's my database is one thing, and the event bus is another thing. So I can't use a distributed transaction, even though I might like to, again, because of reasons of scale and reliability and performance, et cetera. So the producer's goal is to make sure that it updates its local state and also sends the event. Great. Okay, several different approaches. The first approach we'll call change data capture. I hate that phrase, but that is a phrase that enterprise tool vendors have come up with, and that's what people know it as, so I'm going to get on board. Change data capture. So the idea is that the producer first writes its state change to its local database. The database, as part of its doing its databasey job, is going to produce a transaction log, and then somebody on the other end is listening. Maybe we can call it a connector to use Kafka terminology, or some log tailer is going to tail the transaction log, and as a result, send the event. Does it make sense conceptually what I'm talking about? Notice that what we did is we took this thing where we would like to do a distributed transaction where we update our local database and we update the bus in one go. We made it a pipeline or a workflow or a state machine. Does it make sense? Change data capture. In this example, we're going to first update the database, and as a consequence of that, the event gets sent on the bus. We can flip that around where we can do the same thing, but we send to the event bus first. So we send to the event bus first. As a consumer of that event, a consumer updates the database for me and writes that state change. Do you see that these are just the mirror images of each other? Yeah? Great. So this is another technique that we could use. I haven't ever seen this done in practice. I've seen the previous one done a lot, but like the event vendors, Kafka, et cetera, this is a legit technique that they offer as well. Okay, cool. The third approach is if we happen to have the database and the event bus in the same system, we could actually do it atomically with a transaction. So let's imagine that we stored our events in our local database. This is what eBay did, back in 2006. So the state changes and events are actually stored in the same physical repository. So the producer produces the event that goes to the table that stores the state, and it also appends a new event to the end of the event table. And then what consumers do, sorry about that. And what consumers do is they read from the event table. Does it make sense? That's their bus. Okay. The next approach is if that signal system happened to be the event bus itself. So the state changes and events are both living in the event bus, and you could imagine remembering using Kafka or some other persistent log mechanism as your database storage itself, if you're going to do event sourcing or something like that. And then there's another concept or another topic, which is people are listening on those events. So again, do you see that this is the same idea, where either the database is both the data storage and the event mechanism, or the event bus is the data storage and the event mechanism? All right. And then the final approach, which I've also seen done pretty regularly, but it's hard to get right, is the idea of maintaining a persistent local queue that makes sure you do both of them. So the idea here is that we're queuing these local tasks that we need to do to some local thing that's persistent. As a result of that local queue that I've stored to, I'm going to make sure it goes into the database and also it goes on the event bus. And if it doesn't do both, I'm going to keep retrying and retrying and retrying. And the key idea here, though, is that it's persistent, because if I die, I need to come back and that local queue still needs to be there so I can keep retrying. Does it make sense? I've seen this technique done a lot, but without the persistent part, that's not good. In fact, it's so not good that when I go back home to work with my team, I'm going to have to dig us out of an exact problem where we did exactly that. So don't think this is theoretical. This is actually my life. And again, as I will remind you, once upon a time I had hair. Okay, cool. That's the correctness on the producer side. So let's talk about the consumer side. So let's describe the problem. So what does consumer correctness mean? The consumer correctness means that the consumer is going to receive the event and process an action. So it's going to receive the event from the event bus, it's going to do some processing, and it's going to guarantee that eventually it's going to correctly process the event. It might die, it might fail, but eventually it's going to do it. Okay, so these are not individual options as much as they are elements of an overall solution. So the first part is we need to have, if we have multiple consumers, we actually need to have separate clusters, whatever word you want to use, but separate sets of those consumers that deal with each of that consumer logic. So there's a cluster for each one of those consumers, and each one of those clusters has multiple consumers typically to be able to deal with failover and partitioning and redundancy. Does it make sense conceptually what I'm talking about? So if I need to, process an event in two different ways, like I get a new item on eBay and I need to update the seller statistics, and I also need to process the images in some way, like reform them or something like that, those things are logically separate and are in two separate consumers, each of which has multiple instances of the consumer. All right, cool. So that's one part of it, is I need to make sure that I have multiple clusters and multiple instances per cluster for failover. And then the other part is when I get an event, how do I deal with that? So typically this is done as what's called a lease, just like you take a lease on maybe your car or your apartment. And the key part of the lease is that you don't actually own the thing. If you don't pay your bill, you have to give it back. So that's kind of what's going on here. So the idea is that the consumer takes a lease on the event for some period of time. It does the processing that it does. Maybe it stores to its local database, or it does some transaction there, or does some operation there. And then when it is done, the consumer calls back and terminates the lease. And if you're using Kafka, for example, that's what committing the offset is, right? So you're saying, here is the point that I am in the log. I've already processed the event. Does it make sense conceptually? And the key idea of the lease is that if the consumer dies, the bus is going to somehow the system is going to spin up another consumer and make sure it gets processed by the other person. That's why it's a lease and not taking full ownership. Does it make sense what I'm saying? Cool, great. Okay, so again, let's look at it end to end. So the system correctness end to end for an event system requires correctness on the producer side, on the transport side, on the consumer side. Now, careful watchers of this have noticed that I haven't talked about the transport at all. Well, notice that the transport is just a consumer of what the producer does and a producer of what the consumer does. So those techniques that I just said about the producer and the consumer, just reverse those and slot them into the transport part. Did that make any sense what I was saying? The transport is a consumer on the one end and a producer on the other end, and it turns out all the techniques that I just mentioned are exactly the same techniques you would use as a transport. Okay, cool. So if your brain is like, rattling around a little bit, this stuff is hard. This stuff is hard, and what I would strongly suggest is recognizing that there are decades of experience in this area, and a lot of this event-driven stuff, it feels like it's super easy, and this is there's another talk in here somewhere, but there are lots of problems in practical computer science where it looks easy, and 80% of it really is, but the other 20% is nightmarishly hard and was a research problem for PhDs for a while. This is one of them. So what I would strongly suggest is that you use one of these standard techniques and not try to roll your own. Does it make sense what I'm saying? Ditto things like, CRDTs, there's all these different, first order, interesting, cutting edge computer science things where that's an easy problem. Why is that a PhD thesis? And you look and you're like, oh my God, that's really hard at the details. Anyway. So cool. So I would suggest that we resist the temptation to roll your own. If you can get a lot of these guarantees out of an event system or out of a framework, I strongly suggest that you do that because not having to write this stuff yourself is really a benefit. Great. So we talked about migrating to microservices. We talked about the challenges and maybe some of the solutions to how do I deal with data in a microservice world. And then we talked about some ways that we can get end-to-end correctness in one of these event-driven systems. So, achoo.